In this video, we will begin investigating different methods of representing curves. Specifically, we're going to start off by looking at parametric equations to represent a curve. So we say that a plane curve, think maybe the blue curve given here, can be determined by a pair of parametric equations. That is, instead of writing a single function y equals f of x, which would be impossible in this case because we do not pass the vertical line test, what we are going to do is represent the x variable and the y variable individually as functions of t. When we do this, we call t the parameter value, and typically t is going to be in some interval. So this might be something like the interval from a to b. And the idea is that for every value in this interval, there corresponds a point on the curve. So for example, if we know that, let's call it c, is some number between a and b, that will correspond to a point on our curve. The coordinates of that point would be f of c for the x value, because you're plugging in for the function representing x, and g of c for the y value, because you're plugging in for the function representing the y. So to begin, our typical question is going to be, for a pair of parametric equations, can we somehow sketch that corresponding curve, and if possible, maybe represent it with a Cartesian equation, that is, in the terms of a function y equals f of x. So we begin by looking at a very typical example. Plot the given parametric curve, and once we've done so, obtain a Cartesian equation for the curve. Now, how we go about this is really just playing connect the dots in a very methodical way. Since our parametric curve, the t values vary between -2 and 3, we want to just pick some t values that are convenient for us to work with. So that might be -2, -1, 0, 1, 2, 3. Corresponding to each of these values of the parameter t, we'll have a point on our curve. Once we plot those 6 points to the right, we will have a good idea of what our curve is going to look like. So if we look up at our parametric curves, x is t squared plus 2t, y is t minus 3. When we plug in t equals -2, the point that we get is 0 and -5. When t is -1, we get -1 and -4. When t is 0, we get x is 0 and y is -3. When t is 1, we get x is 3 and y is -2. When t is 2, it's 8 and -1. And when t is 3, we get 15 and 0. And we now need to plot these points in the coordinate system to the right. So in this coordinate system to the right, we're going to let each dash in the x direction represent 3 units. And in the y direction, we'll let each dash represent 1 unit. So corresponding to t equals -2, we get the point 0, -5. Corresponding to t equals -1, we get the point -1, -4. And I'm going to go ahead and just indicate what this first point is, t equals -2. For t equals 0, we get the point 0, -3. For t equals 1, we get the point 3, -2. Then 8, -1. And 15, 0, where that 15, 0 is corresponding to t equals 3. So connecting the dots in an intelligent way gives us a curve that looks something like this. And I'm going to go ahead and put an arrow just indicating that as the values of t increases, that would be the direction we are traveling along the curve. So to sketch a given parametric curve, one perfectly acceptable method is to pick some values of the parameter t to get some points, plot those corresponding points, play connect the dots. So let's now go ahead and eliminate what we'll call eliminate the parameter to form a Cartesian equation. And the observation is, when we use the wording eliminate the parameter, what we would like to do is get rid of the t that we see in these equations. So we need to make an observation. So y equals t minus 3 would apply to us that t is equal to y plus 3. So we can take this value that we have for t, it's equivalently y plus 3, and go up to our x equation, and both of the t's that we have present we can replace with y plus 3. We're writing them in this equivalent way. So x is equal to y plus 3 quantity squared plus 2 times y plus 3. And if we go ahead and just algebraically expand, this becomes y squared plus 8y plus 15. And this would be what we would call the Cartesian equation representing the curve. And note, as expected, at least from the look here, we see it's a quadratic function opening to the right, which would mean that it's quadratic in terms of y, and the leading coefficient should be positive.